Hello, we're Team 12. We're representing Project Third Eye, Officer Safety Device. I'm Victor Raymond.
Guillermo, Alvis.
Edwin, Gutierrez. And Matthew, Sosa.
And we're going to explain to you about our senior design. So what is Project Third Eye? It's a device designed to help officers with situational awareness. It's inspired by former law enforcement officers, and we, in the beginning, we came up with two potential design paths, a low-tech option and a high-tech option. And we'll get into why we selected what we did in a minute. So the biggest thing that drove our design and our innovation was a patent. We already had a patent for this design. It was already created and paid for by our company, and so we were kind of obligated to stick within the realm of that patent for the low-tech alternative option. Mirroring that, we decided also to come up with a high-tech alternative option, but we'll get into why we didn't go with that route in a little bit. So why is it necessary? Officer fatalities among accidental road deaths, being struck by vehicles, are almost as common as homicides. The problem's worsening. In this day and age, everybody knows about texting and driving. You've heard the stories, and it unfortunately ends the wrong way, and sometimes somebody ends up paying for it with their life. The most common time for this is obviously when the officers are outside their vehicle, in a pullover type situation, mainly on a main road or something, or a highway. So getting to fatality statistics, if we look here, among officers' deaths, about 14.6%, this was as of the most recent statistic we have, are attributed to fatalities during pullover type situations, from being struck by a vehicle or from being potentially maybe pinched between two vehicles. So it's not an uncommon event to happen, unfortunately. This was as of last year alone, and this is statistics determining that in total about 17 officers have died. Actually, 2 more have died since we got here.
In Florida alone.
Yeah, in Florida alone, since these statistics were posted, 2 more officers have perished, unfortunately, due to incidences occurring outside their vehicles, where they either are struck or, again, pinched between vehicles during a pullover type situation. So our problem statement. We're trying to create a device that not only fits within the patent, but helps officers with potential unseen dangers. Meaning, like, if they're paying more attention to what the suspect is doing in a car when they're walking back to their car than the road, they could potentially wind up being struck. The design also must be really cost effective and universally applicable, because departments have limited funding. They can't invest, tens of thousands of dollars in per car to mount a type of apparatus. It also must notify them to danger seen behind them. So not only being struck by a vehicle, but potentially maybe if a suspect that they're pulling over tries to harm them in any way, it must alert them to that danger. And the last criteria, as I mentioned before, is it has to meet what was already defined in our patent. So our global design considerations. The plan for the company ultimately is to market this around the globe. We met this goal by facilitating user manuals in different languages. So far we have the 3 big main languages utilized around the globe, being Spanish, French, and English. So officers can be trained on how to operate this device in their vehicle. The units for installation in terms of torquing and things like that are all in standard and metric. Again, universal applicability. It can mount just by changing the brackets on the vehicle. You can mount it to any different type of vehicle, because different parts of the world use different types of vehicles as their police patrol cars. And low cost, because not only are departments in America, but global markets where they might not have more advanced alternatives have to be able to afford this product.
For our constraints and considerations, our deployment time should be around 5 seconds. With the desired actuator and the dimensions of our mechanism, that would give us about 1 inch per second. The size limitation, since our mechanism will be mounted on top of the roof, we had the dimensions of the roof as well as the positioning of the light bar, which will give us the remaining area where our mechanism will potentially be mounted. Modes of operation, our mirror mechanism will receive inputs from the pendle switch, the light bar control panel, and the limit switches. These inputs would either deploy our mirror, retract it, or stay in place. The size of mirror was considered for the officers to have a clear and wide view, so the width, the height, and the curvature was considered. Adjustability and compatibility would be on the vehicle's height and also the changes of how the vehicle will be positioned. Based on the environmental conditions and scenarios that the police vehicle can encounter, we needed to select materials that was durable, corrosive resistance, inexpensive, readily available, have easy installation, and a low maintenance. With these materials properties, we selected our components for our mechanism. Throughout the whole mechanism, we used 18/8 stainless steel bolts, washers, and lock nuts. We used aluminum 6061 T6 extrusions for the structure of our mechanism. For the bushings and spacers, we used Delrin for its high strength, durability, and ease to machine. For the rod ends, we used zinc-coated alloy steel. Both these components were combined with PTFE, which reduces the wear and also eliminates the need for lubrication. Now for our mirror. The structure of our mirror was made out of polycarbonate sheet. This was selected due to the high impact resistance. For the officer to have a visual image, we used the mylar reflective film. Design alternatives. We had two options for our design. The first option was mounting the mechanism underneath the light bar. The second option was to mount the mechanism in front or aft of the light bar. We went with option 2 because option 1, we had to remove the light bar, and that exceeded the maintenance and also voided the warranty of the light bar. So that was not an option for us to consider.
So to follow up on what Guillermo mentioned, the design choice that we selected had these features. It basically had a polycarbonate mold that would feature a curvature that would allow for a wider field of view for the officer to have more visibility of his surroundings. Likewise, the Delrin bushings for self-lubrication. It opened towards the front of the vehicle in front of the light bar, simply to avoid any contrast from the lights when they were on. The motion control was controlled by a linear actuator, a ball screw linear actuator that was able to, under a certain amount of load, retract itself in case there was any power failure or anything of that aspect. The logic controller that Matthew will eventually introduce to you was basically controlled by two inputs: the Prendle switch and the operation mode of the light bar. So of course, when the vehicle was in park and the light bar was on, this is the case where we wanted the mechanism to activate. Here are some illustrations of the final design drawings for the mechanism. For the motion analysis, we decided to basically create a slider crank mechanism, which is what basically actuates the mechanism up and down from the linear movement of the actuator. We did a position, velocity, and acceleration analysis from robotics. With those analyses, we were able to find a few singular positions that basically allowed or locked the mechanism in depending on what position it was. That's where that offset came from, to simply avoid that singular position. In the displacement analysis, the actuator moved a total of 4.31 inches per second. 4.31 inches in total, 1 inch per second, which gave the distance for the connector, which we call that point there, the connector, and the mirror, that upper point there, to move a total of 4.71 inches and 25.13 inches. That geometry was simply selected to allow the actuator to have a short stroke to give us the desired final positions that we want. In the velocity analysis, we achieved, with that 1 inch per second actuator speed, we achieved a 3.2 inches per second maximum speed for the connector and a 16 inches per second maximum speed for the mirror, which was well within the ranges that we find acceptable. For the acceleration, likewise, we found 14 inches per second at the connector and 69 inches per second squared at the mirror, at the top of the mirror. For the finite element analysis, we find this necessary for the molds that we were going to design that was going to be holding this mirror. Our worst case scenario basically came from We did a few scenarios of basically a vehicle impact or the mechanism being stuck in its upright position from maybe a foreign object being in its way or something like that. At the end of the day, the worst case scenario ended up being the mirror being stuck up while the vehicle was traveling at a very high rate of speed. The theoretical speed of what the vehicle that we designed it around was 180 miles per hour, which of course is very exaggerated. With that, we were able to derive this 289-pound force just due to the dynamic pressure from the surface of that mirror. This shows the mirror. This is the initial design, which in the rear side of it has a smooth surface. This gave us a 0.62 factor of safety and a maximum displacement of 1.57 millimeters. For the second iteration, we decided to add what's basically fins on the rear surface of it. That basically allowed the load to be distributed among a larger surface. That alone gave us a factor of safety of 2.11 and a maximum displacement of 1.2 millimeters. Some of the static analysis performed on most of the hardware and some of the components came from basic statics. We were able to derive a few equations, and which gave us this linear system of equations. Through a matrix, we were able to solve all of them, and just simple mechanics and materials were able to give us the factors of safety. The lowest factor of safety we found in the entire system was a 4.2, which happened to be on the rod end extensions that we designed. We also went ahead and did a CFD analysis to figure out exactly what were the forces exerted or the pressure exerted on the entire vehicle when this mechanism was in all of its orientations. So with no mechanism installed, with the mechanism lowered and the mechanism raised, these are the pressure distributions across each one. Likewise, these are the velocity distributions of the effects of each one of these cases. This slide speaks of the drag analysis. With no mirror, we saw a 0.49 drag. With the mirror down, coincidentally, we saw that drag lower. And that's simply due to the mechanism being in front of that frontal surface area of basically this light bulb. It allowed for some, I guess, aerodynamic ability for that air to kind of overpass that light bulb. Likewise, with the mirror up, as expected, we saw a very high increase in drag to 0.666.
All right. For the control logic for the device, we went through several iterations, starting with a discrete logic setup initially. One of the things that we found out by doing this is that it's extremely difficult to define a discrete logic setup by hand without introducing extra errors. I ended up using a tool called Logic Friday to help me with that. That was able to reduce the equations down to the minimum number of steps and gates, but it still ended up being an excessive number of devices on chip. From that, discussions with several instructors here at the school, including Dr. Roy, ended up selecting a complex programmable logic device as the final choice for what to use to control the mechanism. Benefits of this are that the device, within reason, is infinitely programmable. A lot of the devices that are out there now, 10,000 plus cycles of programming, mean that even if we have to change the logic at some point, discover a bug, something like that, we can go back and update that on the vehicle without having to disassemble anything and very quickly reprogram it. Additionally, compared to systems such as an Arduino or a Raspberry, CPLDs have a very, very short reaction time. In our case, with a 100 megahertz clock, approximately 10 nanoseconds from input to output. This did, however, necessitate a custom designed circuit board. We worked together to determine all the things that we need to put on the board in terms of inputs and outputs. Like Guillermo and Edwin mentioned, certain inputs. The Prindle switch was park, reverse, neutral, drive, and low selector, and sensitive gear shifter for vehicle. The light bars, the light bar themselves, which is simply a voltage pick from the light bar system, And then there's a simple mode switch that the driver of the vehicle, the officer, has access to, which will allow him to control operation of the switch, or excuse me, the mirror from the vehicle. That allows him to secure it if he wants to, or place it in raise for maintenance. Long term, custom design circuit board is actually relatively inexpensive. Our cost, even prototyping, was approximately, with all components, approximately $45 to $50 per board. Over time, that cost gets cut significantly. Okay. This is the actual circuit board design. On the left is the schematic. This is done in Eagle CAD, and this is the finished solder board on the right. And this is the actual final schematic that we came up with.
So manufacturing, this is one of the biggest things that's overlooked often in designing and creating things, because if you can't actually produce the product you want for a reasonable price, then it becomes not a product worth having. We decided if we could not machine the product, most of the products ourselves, aside from what Matthew was saying, the logic board that we had printed, the rest of the components, though, in order to keep our costs down, needed to be able to be manufactured in-house. So using FIU's machine shop, which they have here so graciously, we moved into producing the different components. So here we have starting the milling process of all the different control bars and control arms. They were able to be done on just a standard Bridgeport mill. If the product was to be marketed, we'd probably move towards casting, and then maybe a finish of machining of milling. That would facilitate cheaper overall costs. Here we have Matthew and Guillermo doing the Delrin bushings. They were all lathed out to the required specifications as dictated by the CAD. It was a very short process because Delrin's a very easy material to work with. However, in the final type of project, you would be looking at having these injection molded, and then that way it would save a lot of time. Here we have Edwin assembling the different mechanisms and putting the bushings where they belong into the tracks. Here we see the completed side of one of the sides of the mechanism. Here I am putting the film on the prototype mirror. Again, to keep costs down for the prototype, we went with a polycarbonate sheet and Mylar film. I know tinting, so it was able to create a mirror. And it's a high functioning mirror. I was a lot happier with it than that. And Matt, if you want to talk about
this is actually one of the initial stages of prototyping the circuit. The chips in the center are all discrete logic chips that were used to set up the circuit. And then the last bit there is just installing the brackets and mechanism.
Yeah, the only issue we ran into was actually the brackets. That is because in traditional, like for light bars and light bar companies, they would have a 3D scanned image of the car, and they would be able to get the actual custom bends on these pieces of metal. We were working by hand, so some of our brackets are a little taller than they should be on a final or finalized product. This can be easily adjusted by the company though. The scans are readily available online. With regard to our mirror, in theory and the final product, you wouldn't have these metal arms here. You'd have a solid piece of polycarbonate with the arc that we are already looking for, as well as an embedded piece of aluminum inside the polycarbonate, which would facilitate the points, the actuation points. That would give the mirror its structural integrity for actuation purposes, as well as it would cut down on cost and weight slightly. And it would facilitate a closer hug to the surface of the roof of the car, which is the ultimate goal, is that this thing is supposed to be as close to the curvature of the roof of the car as can be. Here we have a demonstration of the actual mechanism actuating. Embedded. You have to enable editing.
And enable content.
Sorry. So in this video, I'm actually manually operating the mirror using the power wires. Unfortunately, despite best guess, over 150 hours at minimum between working on the control board and the programming for this, I haven't gotten it to work yet. It's actually something I'm not happy with. But it is on our list of future work, is getting that to work.
So for the prototype costs, we were able to keep it fairly low. The most expensive item on our list was the actuator. This has to do with the fact that we use a standard industry actuator. If this mechanism was to be actually bought, you'd get an actuator that would be developed to match more closely what your specifications are. This one, we picked it because of two features. One, it's fast deployment and retraction time, and its ability to be pushed down due to force. So if it did get stuck up in a worst case scenario and the car started driving, the actuator would actually wind back down and the mirror would deploy back into the stowed position. This would prevent breakage of the mirror or damage of any of the components. The other thing is that the PCB boards, they were pretty cheap in total once all said and done. And the last was more or less miscellaneous components, was the actual subcomponents for the PCB board, capacitors, resistors, the different chips, the MOSFETs and whatnot. And the acrylic for the mirror was fairly minimal too. So again, this is for the prototype. Actual cost of a real mechanism should be able to be reduced by at least 10 to 20% because a lot of these components would be pre-manufactured as opposed to done by hand. The boards would be print and play from the manufacturers. And thank you.
Comments, questions?
I have some questions. The first one I want to ask is pinch points. Concern.
Absolutely. In fact, to give you, we didn't do it, thankfully. I always made sure everybody's out of the way when we're operating, but that actually just got a running force of in excess of 500 pounds. You stick your hand in there and you'll lose it. That is definitely a concern. It's on the list of
So shielding of some
absolutely.
sort?
Well, what the final intention is that these two bars will be enclosed in a effectively an aluminum enclosure or steel enclosure once they're on the vehicle, so that there's not a way for you to get anything in there where it can pinch. The polycarbonate will be somewhat forgiving if you stick your hands in there, but definitely going to make sure that there's at least 3/4 of an inch, maybe a little bit more space in there, so even if you put your fingers in there, it's not actually going to pinch you. In fact, in this case, we actually do have about that much space there. I wouldn't want to try to put my hand in there, to be perfectly honest. I stuck my hands in some dangerous places like you saw in the little picture there. And I'm used to it, being a Samaritan, but I wouldn't want to do that.
Okay.
Absolutely.
And then the second question I want to throw out is tied to the impact that the environment is going to be in. You're talking about polycarbonate.
Yes, sir.
And you make sure it's UV cured
Absolutely.
so that she survives. Also, you said you're using aluminum extrusions, and then you showed me some nice stainless steel screws, which says to me a galvanic series problem.
Correct.
So you might want to think about trying to do stainless with stainless or aluminum with aluminum so that you don't have that issue moving forward.
Absolutely. Galvanic corrosion it's on the list, but for prototyping it was much.
No, I understand, but when you go out and do it as a as something that's going to be for sale,
Yes.
for sure you need to know that. And then when I saw your model going up there and you put it down, that's pretty flexible.
Yeah, this polycarbonate was just for us to work with. It's very malleable and very. We weren't sure exactly. We did math equations and physics equations on angles for mirrors to achieve the best angle. However, until you facilitate it and put it in person and see what the image looks like, you can't be sure. So rather than try and do our initial thought was to actually do maybe like a carbon fiber and then lay like a mirror on top of that, so a carbon fiber type mold to represent the polycarbonate structure. However, because we weren't quite so sure, the easiest method to get the best angle and to find the best view angle was to do it out of a thinner plexiglass and then keep it flat and then push it until it gave you the desired arc. So in the future, the actual development of the product, we will suggest this curvature as our optimal curvature, or maybe even do more work into finding if there is even a slightly better curvature out there.
Yeah, because when I think about 95-mile-an-hour car flying down the road, this becomes a nice wing pretty quick.
Absolutely. The goal would actually be to give it a curvature as close to that of the roof as possible, which means that the front edge of it will actually be down slightly. So it'll actually give you, like Edwin said in his CFD analysis, it actually does help to keep the mirror
Up and
down
over,
as opposed to and slightly more distracting. I still find it interesting, but it does actually help to keep it from turning into a wheel.
Very good, thank you.
No problem, sir. Yes, sir.
I wanted some clarification. You mentioned, or you did some analysis as if the mirror was left on its deployed position.
Correct.
But then you mentioned something that the actuator would not be strong enough to uphold the wind, so it would collapse. Am I getting that wrong? Or?
So,
Well, I guess that case would be due to like a foreign object being somehow stuck in the mechanism and making, overpowering the actuator and holding it up.
Yeah.
That was for a very specific case.
What I had mentioned had
too.
been like hypothetically say the mechanism deployed and say maybe the wire fried, something happened, and you lost electrical power. That means
you could have the mirror deployed while driving.
You could do it. It could happen. Murphy's Law says that it will happen at some point.
So
the goal, selection of an actuator for production. I've talked with Lori, one of our sponsors, about this. In selection of an actuator, we want the motion of approximately an inch a second. More is better, but if we can't, this actuator's got a 560-pound kinetic holding or kinetic force, 3,000 pounds of static holding force. So it is not going to let the mirror down. However, the final actuator, about an inch, inch and a half, somewhere in that range, 100, maybe 150 pounds of kinetic force at best, and then a static holding force way less than 1,000 pounds. Whether that's with a clutch that we have to put in there or just gear slip. Then really a clutch, and gear slip, that's bad. With that there, the wind will push it down. Because like Edwin said, it's I think 1,800 pounds of force, something like that. Because now granted, the police vehicle's not traveling 180 miles an hour. We selected that to be more than generous with the forces that we were going to see. In reality, I think 135 miles per hour current top speed for police vehicles is more than norm. It will be lower than that on a lot of vehicles.
So I have cleared up. I have 2 recommendations.
Yes, okay.
One is if it is left up, we saw in a previous project that headlights could reflect fairly well, and now you have a mirror where at night you could have oncoming traffic having reflective lights bouncing off of this.
Okay.
Just like I said, so keep that in mind. Second thing is if you have it deployed up, you are prone for FOD, foreign object damage, where you could be cracking this. So when you do the material selection, I would recommend something similar to safety windshields, where it might crack, but it won't send all of this glass flying into the traffic behind you.
Yep. So to answer those 2 points, with the mirror being at a 90-degree angle to the ground, which is what the goal is, your headlights would actually be reflected up. So it should alleviate most of it. It won't be all of it, absolutely.
All I'm recommending is check it.
Yes, sir.
Whoever grabs on or continues this project, check it. Park a car in front of it, see if there's any blindness that might come from a car, whether it's an SUV or a car or a truck, whatever. It's just a constant consideration, that's all I'm saying.
Absolutely.
Again, when it's propped up, you did static analysis. I would recommend doing some sort of vibratory analysis, especially with something that's going to be moving in and out that would deteriorate the life of your actuator as well as your structure. And something I would have liked to see is we did drag analysis. Maybe something that the police would like to understand is translate that drag analysis into a miles per gallon impact.
Okay.
That's something that they would be more familiar with than a drag component or a drag number. Yeah, that's. I mean, these are just recommendations, and something to keep in mind is you did all the right testing for your project, but you forgot the most important test, which is, does it work?
It does.
So it does.
Absolutely.
Have you identified what's the operating distance?
So actually, lawyer was there for part of that testing. When we had the mechanism, actually, I think the same day we shot that video, we actually got with, I think it was Victor and I.
Myself at like a 10 to 15 foot range from it, but staggered as if I was walking back to the car on the side that a law enforcement officer would be walking to get into the vehicle. And with Edwin appearing out about 40 feet behind me, which is even a further distance than you would normally see, I was still able to clearly identify his face. I was able to identify what he was doing with each hand, up to the point of how many fingers am I holding up. So it does provide enough visibility and enough ability for an officer to at least be able to determine in a split second what's happening behind me. If I were just to glance up, I can see clearly if an individual is getting out of the vehicle, if an individual threw something out of a vehicle, like you could see those things. Granted, it would be more one of those, the whole intended goal is that this is a peripheral grab, meaning like you're not staring at this, because if you just stare at it, it defeats the purpose of staring at traffic and keeping yourself safe. But you could definitely see fast motion behind you and definitely make a kind of decision on what's happening behind you.
So I would put that in your report as
Yep.
one of your results.
Definitely.